Hello everyone, thank you for coming to my presentation. The title of my work is Student Tutor Makes the Initiative Decision-Making, supported by Deep Reinforcement Learning. My research is focused on pedagogical decisions on intelligent tutoring systems. As we know, intelligent tutoring systems are highly interactive in learning environments to support student learning by making many personalized, hopefully effective pedagogical decisions such as when to provide hint, what to present, and how to present next problem. Generally speaking, most of the pedagogical decisions on ITS are made by tutor. We refer it as tutor-driven. More specifically, the tutor-driven decisions can follow expert rules designed by human or some data-driven approaches induced by machine learning methods such as reinforcement learning. On the other hand, there are certain decisions can be made by students. A lot of research have shown that give students the control of their own learning could improve their learning performance. But it is not always true because some students are not good at making decisions. Therefore, our research question is how to give students the control of making their own decisions while keeping the decisions effective. To do so, we proposed a general student tutor makes the initiative decision-making framework. In this framework, student is the front-end decision maker, while pedagogical agent provides back-end support. The ultimate goal of this framework is to strike a balance between giving student a sense of control over the learning process while supporting effective decision-making. In our framework, the pedagogical agent will only intervene and give explanation when student makes a suboptimal choice on a critical decision. Otherwise, the student decision will always be respected. Here, intervention means that the tutor will carry out the pedagogical agent's choice. A lot of research have demonstrated that pedagogical agent can be effective in improving students' learning, so their decision is effective and optimal. And before the intervention, the tutor will explain to student why the alternative choice is better, which aims to smooth the student-tutor interaction. In this study, we compared our student tutor makes the initiative framework with an expert policy where all the decisions are determined by tutor. Our results showed that the students in student tutor makes the initiative condition performs significantly better than the students in the expert condition. Then we conducted an ATI effect analysis. Previous research showed that some students who are more actively involved in deciding what and how to learn will benefit from the sense of control because they are more engaged and motivated in making decisions. We refer them as high performers, and their performance is similar to the tutor-driven peers. On the other hand, not all students are adept at making decisions. Some students are lack of metacognitive skills to make effective decisions, so that making decisions would hurt their learning. We refer them as low performers, and when they make decisions, their performance is worse than their tutor-driven peers. Then in our study, the results showed that both high and low performers benefit from our student tutor makes the initiative framework, that high performers outperformed the expert peers, and the low performers catch up with their expert peers. This is the outline of the following talk. I will start with identify critical decisions. It is hard to define critical decisions directly, but it is easy to ask by comparing critical versus non-critical. By name, critical decisions are a series of decisions have great impact on the desired outcomes. The non-critical decisions are those have weak impact on the desired outcomes. So now, the challenge is how to identify critical decisions from non-critical ones. We can visualize the problem in this graph. First, for any given state, it can be critical or non-critical. If the state is critical, then there are two types of actions on it: optimal action or suboptimal action. Based on our definition, on critical state, choose different actions will have great impact on the final outcome. Thus, optimal action should be taken on the critical states. Then for the non-critical states, choose different actions has weak impact on the final outcome. So any action can be taken on the non-critical states. Therefore, there are two factors in the critical decision: identify critical state and select optimal actions. To do so, we leveraged a critical deep reinforcement learning approach. In this critical deep reinforcement learning approach, we use long short-term rewards to identify critical states and deep Q network to select optimal actions. More specifically, in the long short-term rewards, the long-term reward is Q-value difference from critical DQN policy, while the short-term reward is the inferred immediate rewards from InfraNet model. For the standard DQN, it follows the original Bellman equation that the Q-value is calculated by the immediate reward plus a discount factor gamma times the maximum Q-value in the next state as prime. For the critical DQN policy, we modified the Bellman equation to consider the criticalness of state, that the maximum Q-value is considered in critical states, while in non-critical states, the average Q-value among all possible actions is used. Next is the policy induction. To induce the DQN and critical DQN policy, our training dataset contains more than 1,000 students from 7 semesters. There are 142 state features, which can be characterized into 5 groups. There are 3 actions in the problem level and 2 actions in the step level. The delayed reward is based on normalized learning gain. In this study, we compared our student-tutor mixed initiative framework with an expert policy. In the STMI policy, students are the decision makers that decide what action to take next. In the meanwhile, we followed our critical deep reinforcement learning approach to identify critical state and select optimal actions. So, after students making their own decisions, if the state is non-critical, the tutor will take student choice. If the state is critical, we compare student choice with the critical DRL choice. If they are the same, then the tutor will carry out the student choice. Otherwise, the tutor will give an explanation to student and then carry out the critical DRL choice. For the expert policy, the tutor always takes random actions. In our study, we focus on the decisions among 3 pedagogical actions. In worked example, student observes how the tutor solves a problem. In problem solving, the student solves the problem by themselves. In faded worked example, student solves a portion of steps in a problem, while the tutor solves how to solve the others. In order to make the student-tutor interaction smooth, the explanation message is designed to contain 2 short components to illustrate the reason and outcome behind the tutor's decision. For the reason, we mainly focus on the efforts and time, while for the outcome, we told the student what is the actual action to be carried out. This table shows some examples of the explanation messages. For example, we are good on time, to learn more efficiently are the reasons, and let's work together on this problem and try to solve this one yourself are the outcomes. It is important to note that each type of intervention has multiple explanation messages, and the tutor will randomly select one to show to students. Next, I will introduce the experiment setup. Our ITS is called Pyramis, which is a web-based ITS teaching college students probability. It covers 10 major principles of probability such as the complement theorem and Bayes rule. This is the interface of our parent tutor. In the classroom study, the participants are 153 undergraduate students in 2024 semester. They were randomly assigned into the two conditions, and finally, 105 students completed the study. A chi-square test shows that there's no significant difference between the two conditions on the completion rate. In the classroom study, there are 4 phases: pre-training, pre-test, training on parent tutor, and post-test. The only difference between the two conditions are the pedagogical policies deployed in the tutor. Note that there are 14 questions in the pre-test, but in the post-test, we have 14 isomorphic questions and 6 additional complicated questions. Next, I will show the results. First, we compared the pre-test scores between the two conditions. The result showed that there's no significant difference between the two conditions. It means that the two conditions are balanced in terms of incoming competence. Then, within each condition, we compared the isomorphic post-test scores with their pre-test scores. The results showed that the isomorphic post-test scores are significantly higher than the pre-test scores in both conditions. It means that our tutor could improve students' learning regardless of the policies deployed. Next, we compared the learning performance between the two conditions. The result showed that the student tutor mixed initiative condition significantly outperformed the expert condition on both isomorphic NLG and full NLG. It indicates that our student tutor mixed initiative framework could significantly improve students' learning gain than the expert policy. In order to measure ATI effect, we further divided students into high and low groups by a medium split on their pre-test scores. First, the 2 low groups and 2 high groups are balanced in terms of incoming competence. Then, for the learning performance NLG, there's no significant difference between the 2 low groups, but in the 2 high groups, the student tutor makes the initiative condition is significantly better than the expert condition. Finally, there's no significant difference between the 2 low or the 2 high groups in terms of training time. Then, we analyzed the critical decisions in the student tutor mixed initiative condition. We found that high students experience the more critical moments. They are able to make optimal choices, but also they often choose suboptimal actions and received more interventions. Next is the conclusions. In this study, the results showed that our student tutor mixed initiative decision-making framework is effective in improving students' learning. Also, it reveals that the framework can assist high performers to achieve better outcomes than expert policy, and offer low performers the same benefits as the expert policy. That's all. Thank you.